All right, friends. So now that you kind of know what the bell curve looks like, the normal distribution looks like, we have to adjust. And this is going to seem a little bit strange because we're going slightly out of order with how I would do it in class with you, but that's okay. We'll get the main idea. That horizontal axis that I mentioned, the z's, that z only is called z on one particular curve. As I mentioned, it's the standard normal distribution. The problem is that we have many kinds of distributions. The standard normal, as we mentioned, has an average of 0 and a standard deviation of 1. I can't think of anything that has an average of 0 and a standard deviation of 1. There's just nothing that exists. However, one of the programs I gave you, STNormal, and we'll play with this in class on Wednesday, assumes, the reason it's called STNormal is because it's a standard normal distribution. So it assumes that you've got a standard normal distribution. Now the beautiful part about this is you can actually standardize any distribution, although we're going to put the word normal in there, not just any distribution, but a normal distribution that has an average of mu and a standard deviation of little sigma by this simple little calculation here. All you've got to do is take whatever the raw score you have is, subtract the mean, and divide by the standard deviation. And in class, I'll explain this much more detail. But this is one of those rare formulas in this class. I know I've been very proud about the fact of not using all that many formulas with you in this class, although this is a very important one. So we'll talk more about it in class. But essentially, what that does is it converts any raw score into what's called a z-score, and a z-score is simply a number of standard deviations from average. The further you are away from average, the more unusual the result. So by the time you're done this is kind of a ghetto PowerPoint, I apologize. The z-scores that you have will be standardized, which means they'll have that average of 0 and a standard deviation of 1. Now I put why do we need this? So here's a research question for us. Mark Spitz, 1972 Olympic swimmer, 7 gold medals. Michael Phelps, 2000, I believe this was 2008. He won 8 gold medals. I don't have the data from the most recent Olympics that Phelps was in, but we can use 2008 as a good comparative. Who's more impressive, Spitz or Phelps? Well, Spitz got 7, Phelps got 8. Phelps is more impressive because he got 8, right? Well, that's one way to look at it. Another way to look at it is, well, yeah, he got more. What were his medals in compared to Spitz? And that's, I think, a fairer question. I believe that is a fairer question. As it turns out, both Spitz and Phelps competed in, they medaled in 3 of the same events, 2 butterfly events and a freestyle event. We're going to analyze those 3. We're not going to analyze the events that they didn't compete, if you will, quote unquote, head to head in, decades apart. So what I've got here is the men's 200-meter butterfly. This is the final event, the final times of the men's 200-meter butterfly. Okay, so I've got on the left Mark Spitz's times from 72 and where he fell in the distribution. He had a time of 2.12 minutes. Phelps had a time of 1.867 minutes. So you say to yourself, well, clearly Phelps is a more impressive butterflyer, because he had, 2/10 of a second, maybe 1 to 2/10 of a second advantage over, 1 to 2/10 of a minute advantage over Phelps. That's an eternity in a sprint speed like the 200 butterfly. But then you say to yourself, wait a minute, hang on. You can look at Spitz versus Hall, which is second place, and say to yourself, well, look at the difference between first and second here and first and second here. Spitz blew Hall out of the water. So Spitz is more impressive than Phelps, comparing Phelps going against Laszlo. And then you get into this this statistical fist fight, saying, well, who's more impressive? Phelps has a lesser time, but Spitz has a bigger gap to Hall. It would be helpful if we could somehow compare them both on the same, if you will, axis, the same comparative measuring stick. And that's where z-scores come in. So what I did down here was I calculated the average time it took for these 8 gentlemen to finish the 200-meter butterfly in 1972's gold medal round, and the average time it took in 2008. Also a standard deviation for those times. Notice the standard deviations are very close. Very close. The averages, definitely, they're different in roughly the same amount that Spitz and Phelps were different. Okay, so far? Okay, so far. Another thing that's often noticed is Nikolai down here, even in last place, was above Spitz in first place in 72. And a lot of this is due to training, technology, the new fancy shark suits they wear, quicker than skin suits. So again, all the more reason to get some kind of a standard ruler of measurement. And that's where the z-scores come in. So here's Mark Spitz's z-score. I take his finishing time. That's what I call his raw score. I subtract the average length of time from his round and divide it by the standard deviation of his rounds, and I get negative 2.01. All that means simply is that Mark Spitz, his time is 2 standard deviations below the average of 2.066. And I encourage you to check that out. If you double 0.027, you get 0.054. If you take 0.054 away from 2.066, you get roughly what Spitz's time is. This is the same mu minus 2 sigma we've been doing for weeks now. Fair enough? Okay. So Spitz, 2 standard deviations below average. A similar computation for Phelps using the average and standard deviation from the 2008 round shows that Phelps's time of 1.867 was only 1.62 standard deviations below average. So they're both below average, obviously, because they both won their rounds. But Spitz, from a comparative standpoint, is more below average because he's a further standard deviation measure away. If he's a further standard deviation measure away, that means it took him less time comparatively when you weight it for the performances in his heat in 1972 than it took Phelps in his heat in 2008. So my vote is in the 200-meter butterfly, Mark Spitz is the more impressive butterflyer. I did a similar analysis in the other 2 events they competed in together. In the 100 fly, Spitz's z-score was a negative 1.68, where Phelps's was a negative 1.4. Which means when in the more of a sprint distance, neither of them was as impressive as they were in the slightly longer distance, but they're still both well under average. And I would again give Spitz a higher, if you will, impressive rating because he's further under average than Phelps is. But in the 200 free, Spitz negative 1.34, Phelps almost negative 2. So what happened here is they flip-flopped around from the 200 fly. Now Phelps is more negative, which means Phelps is more impressively under average than Spitz, which makes me claim that Phelps is a more impressive 200 freestyler. So if I had to make the call on these 2 gentlemen, I would say Spitz is the more impressive butterflyer, and Phelps is the more impressive freestylist. But you know, compared to how I swim, these guys are both Evinrude engines in the water. But to be that as it may, the point of this is that with this beautiful little formula up here, with this beautiful little formula right here, let's zoom in on that bad boy. Whoa, hello. With this beautiful little formula right here, we are able to convert any raw score from any distribution into a standardized, normalized score that we can then compare to any other raw score from any other distribution using the same ruler. And that's pretty rad. And that's what we're going to spend quite a bit of time in class doing on Wednesday. All right, we'll catch you guys then.